So let's apply this formula. Right now we only have one formula for geometric. It's great, we need to use it. Given the geometric sequence, determine the desired term. So we have 3, 6, 12, determining T7. So term 1, again, fairly easy to pick off. Term 1 is 3. Common ratio, well, let's use this little formula we have at the top here, Tn over Tn minus 1. Let's pick any term, I don't know, let's pick term 3, which is a 12, divided by the previous term is 6. Surprise, surprise, the common ratio is 2. Again, you could probably pick that off by saying 3 times 2 is 6. We are looking for term 7, and n is 7. So T sub n is T1 r to the n minus 1. T7 is 3 times r, which is 2 to the 7 minus 1. Again, when you make replacements, make sure you put stuff in brackets. 2 to the power 6 is 64, and 3 times 64 is 192. So the term 7 is 192. How about the second example here, 1b, 81, negative 27, 9. So term 1 is 81. Common ratio is, well, let's go with negative 27, term 2 over term 1. You should be able to notice that 81 and 27 are both divisible by 27, or I mean you could reduce it, divide by 3 kind of idea. We end up with negative 1/3 as a common ratio. I like the idea of sticking with fractions. T6 is what we're looking for, and n equals 6. Why don't you hit pause here and see if you can solve this formula. The term 6 is what we're looking for. 81 is the first term. Common ratio of negative 1/3 to the 6 minus 1. So 81, negative 1/3 to the 5. 81. Now, a negative sign raised to an odd power is still negative. 1 to the power 5 is 1. 3 to the power 5 is 243. You certainly could put this in decimals. I think we need to move on maybe a little bit, be able to reduce these things. 243 is a power of 3. 81 is a power of 3. You should be able to reduce this to negative 1/3. So term 6 here is negative 1/3. Moving on, I'm going to get a little bit tougher here. Given the geometric sequence 64, 96, 144, determine which term in the sequence is 729. So, term 1, again, 64. Common ratio, starting to get a little bit tougher to just pick off, so this is definitely where we should probably look at a formula. Our term 2 divided by term 1 will certainly work. If you roll that through your calculator, you'll end up with 1.5. Certainly you could do it as a fraction, 3/2, but 1.5 is a nice exact answer. Term n is 729, we don't know that, and n is what we're looking for. So let's slot this in the equation. 729 is 64, 1.5 to the n minus 1. Basic algebra tells us we need to divide by 64 first, and we end up with a pretty crazy decimal value here, but I'm going to write out the first couple terms, or first couple decimals. Make sure you write out as many as you can, and that's 1.5 to the n minus 1. Now we're at a bit of an impasse here because algebra now tells us we somehow need to get rid of this 1.5, which is a base of an exponent. We don't really have the tools for that. We're a little bit lucky though that the n value has to be a positive integer. N must be a positive integer. Why is that? Now remember, n represents just its location in the list, the term number. The only term numbers we have are things like term 1, 2, 3, 4, etc., etc., etc. So n has to be a positive integer, and our only option here when you're trying to solve for a power so far is we must use guess and check. Or we could call it Goldilocks and the Three Bears method. Why do I say that? What we're going to do is we're going to take 1.5 and just guess at what the power is. Let's say the power is 4. Well, run 1.5 to the power 4 through your calculator. You get 5.0625, etc. This is too low. We need it to equal 11.39. Let's try again. Let's try something higher. 1.5 to the power 7. 17.086. Oh, this is too high. Let's try something in between. How about 1.5 to the power 6? 11.3906. Oh, look at that. That's just right, says Goldilocks. So the power is 6. So that's 11.390625 is equal to 1.5 to the power 6. Therefore, we use this little triforce of dots. The power of 6 has to equal the actual power that we had, which was n minus 1, and we get n is 7. This might be a whole lot of kind of guess and check work, not very specific, not very rigorous. You may want to take that n equals 7 and just back check, plug it back into the formula, and make sure it works. Geometric sequence has term 2 equals 10 and term 5 equals negative 80. Determine the common ratio. This tends to become a little bit more of a difficult problem than arithmetic for sure. We could write the two equations for these. We have term 2 equals 10. So 10 equals term 1, which we don't know, times the common ratio, which we don't know, to the power 2 minus 1. Term 5 is term 1 r to the 5 minus 1. So we have a system of equations. And what we could do is we could solve for either r or t1 and plug it into the other equation. That works just fine, but I want to talk about something which I call a bit of a slots kind of idea. Let's actually write out the slots involved for specific terms in the sequence. There's term 1, I don't know what it is. There's term 2, it's 10. Term 3, I don't know. Term 4, I don't know. Term 5 is 80. If you'll recall from arithmetic sequences, how we move from slot to slot or from term to term is by adding. In this case, since we're talking about geometric, each hop along the lily pads here is an extra multiplication by r. So we can kind of pen our own little formula. 10 times r 3 times, or r cubed, has to equal negative 80. R cubed is negative 80 over 10, which is negative 8. And the cube root of negative 8 is negative 2. And there's our common ratio. Remember, when you take the cube root, fifth root, seventh root, odd roots, you preserve whatever the sign you're taking. If you're taking the square root, fourth root, sixth root, even roots, you have to put in a plus or minus to indicate that it could have been the positive or negative root. Example 4. We have term 3 equals 18. Term 5 equals 648. We could, much like the question above, go into a system of equations to figure out some information. Again, let's maybe take a look at doing slots here. Term 1, term 2, term 3, term 4, term 5. Why don't you take a moment, hit pause, and try and find the common ratio. If we take a look, we have 2 hops along our sequence here, so that's going to be r squared. We can write out a little formula. 18r squared is equal to 648. If we divide by 18, r squared is going to be 36, and r is 6, but don't forget that it should have been plus or minus. Again, we've taken the square root. To continue on with this, we could solve for T1 by taking term 3 equals term 1 plus or minus 6 to the 3 minus 1, and continue on for there. Find term 1, then go back and find term 2. Another option is to go back to our slots idea and if we think from term 3 to work backwards to term 2, we are going to divide by r. So previously, to move right, we multiply by r. In this case, we're dividing by r. So a fairly simple formula would be term 3, which is 18, divided by the common ratio, which in this case could be plus or minus, so this is an alternating sequence, and that's going to equal term 2. Certainly term 2 is 18 divided by 6 is 3, and it could be positive or negative. Thus ends the examples for sequences and series geometric sequences.